All right, welcome to Chapter 6, Part 2. So before we jump into the types of reaction mechanism steps that you might see, we have a couple of vocab words that we need to define, and that is nucleophile and electrophile. We will be using this terminology a lot. Most of our reactions are driven by opposites attracting. Negative areas of negative or areas where there's more electron density, being attracted to areas where there is less electron density, right? This is something we have learned for years. Opposites attract, right? This is what we know about when we think about magnets, when we think about intermolecular interactions, right? Positive and negative attracts. And so when this is all just review over here. Negative is attracted to positive. So things that are electron rich are going to be attracted to things that are electron poor or electron deficient, right? So we will see attractions between things like things with full charges, but also things with partial charges. So you're looking at chloromethane on that slide. And we know that the carbon-chlorine bond is polar. Chlorine's more electronegative. So you wind up with a molecule that has a partial negative side and a partial positive, right? When we look at something like, so in this case, we would say this carbon is electrophilic, right? So electrophilic or an electrophile. This carbon equals an electrophile. So let's think about what that word means, right? This means electron loving. Something that loves electrons, right, is attracted to electrons, is attracted to negative charge, must be positive because opposites attract, right? Electrophile, electron loving. That means it is going to be also electron deficient. It will be positive in some way, either partial positive or fully positive. And because we are organic chemists, we are often talking about carbon. So we are looking at examples in which carbon can be electrophilic, or next where it can be nucleophilic, right? So when we talk about an electrophile, it is important that you understand that means it's electron loving because it is electron deficient, because it is partially positive. We see that a lot with carbons connected to electronegative atoms like oxygen, chlorine, fluorine. Now, we are also going to deal with some compounds that look like this. We'll see magnesium a lot towards the end of the semester, but let's talk about the example that's on this slide. Now, for one, you're seeing something that might be surprising to you. Lithium is a group 1 metal. Carbon is a nonmetal. And yet we have drawn a covalent bond. So a lot of times what you learn at least in Gen Chem 1, I know, is that a covalent bond is between nonmetals and an ionic bond is between a metal and a nonmetal. And that is a great starting point, but it's really more of a spectrum from ionic character to covalent character, and it has to do with the difference in electronegativities. And so when you think about, like, fluorine has a electronegativity rating of 4 on that Pauling scale, and lithium is somewhere below 1, right? That's a really big difference. So the fluorine really does take all the electrons from the lithium for that bond. Carbon has a rating, I believe, of a 2.5. So it's still significantly higher than lithium, but the difference isn't as great. So this has less ionic character than, say, a lithium-fluorine bond, and more covalent character. But it's still going to be very, very polar. Carbon is much more electronegative than lithium. So whether we draw it like this or we draw it like this, it doesn't matter, because the point is the carbon is electron dense, right? As opposed to what we saw on the last example over here. Right? The carbon is taking that electron density, right? If we think about it in terms of that covalent compound, now the carbon side has the partial negative, the lithium has the partial positive. This is showing us that this carbon is nucleophilic, right? So let's think about that word now. We know electrophilic means electron loving. Nucleophilic, sorry, it's NEU. Nucleophilic means nucleus loving, right? But what is that really telling us? Nucleus loving, it's not so much the nucleus that it's attracted to, but what do you know about the charge of a nucleus? It means positive loving, right? Well, what's going to love something with a positive charge? Something that's negative, right? So a nucleophile is going to be attracted to positive charge because it's negative, right? Because it has a negative charge. And because so many of the steps that we are going to be looking at as we continue through our journey in organic chemistry and organic reactions, so many of the steps, so many of the reactions are pushed forward because of a nucleophile being attracted to an electrophile. So this vocabulary is important. You will be quizzed and tested over it, if not specifically in a fill-in-the-blank question, but it'll be tested by just using those words in questions. So these are very important vocab words that you need, right? So if you continue to go through your slides here, just other potential things to look for nucleophiles, right? It's going to be anything that is electron rich, something that can donate a pair of electrons. So when you're forming a new bond, nucleophiles are really important. It can be a covalent bond that is just very polar. It can be a full charge, like on an oxide ion. It could just be a lone pair on an electronegative element. And in some cases, something we're going to talk extensively about in chapter 8 and 9 is think about all that extra electron density in a multiple bond. So a lot of our reactions of double and triple bonds push forward because of all of that electron density in that multiple bond, right? Lots of electron density, very negative, makes it a good nucleophile. Right? When we think about electrophiles, the obvious thing that you might think about would be just a full positive charge, right? If there's a positive charge, there's a very obvious lack of electrons. But we are also going to see, especially in chapter 7, the carbon attached to halogens is a good electrophile because the halogen is so much more electronegative. Right, and this is a good point before I move on. Electrophiles are good examples of Lewis acid. So it's not that we are changing any definitions. This is just a broader term that we will be able to use more frequently, even when we're not dealing with acid-base reactions or Lewis acid-base reactions. Okay, so this is just some practice here. You will get some practice in your homework, identifying nucleophiles and electrophiles, and I certainly recommend popping into chapter 6.7 and looking at some skill builder problems within that online text on Wiley Plus if you're having any trouble with this concept. Okay, what the majority of this video is going to be about, however, are mechanism patterns. All right, so every reaction has its own mechanism, right? How we get from start to finish, what bonds break, what bonds form, in what order, what intermediates are made. And oftentimes there are going to be recognizable patterns. So when we talk about organic compounds, there are millions of organic compounds. When we talk about the reactions of organic compounds, There are so many that we could spend our entire career just studying each one individually. So what do chemists do? We group things based on patterns. That's why we start off learning functional groups at the very beginning, because it's much easier to learn about a type of reaction, a type of pattern, a type of functional group than to learn about every specific compound and every specific reaction for that compound. And so to start us off, we're looking at very general mechanism steps that you are going to see over and over again in different combinations. So we start off with a reminder about curved arrows, right? Curved arrows are showing how the electrons move. You had a question in exam 1, if you were in my fall 2021 class, where I showed a mechanistic step for an acid-base reaction where one of the arrows was wrong. And it was the direction of the arrow. A lot of times, because we are saying here in this acid-base step, right, the base is accepting the hydrogen. So you're thinking about the proton or the hydrogen moving towards the base. But the arrows aren't built to communicate atoms moving. The arrows tell us where are the electrons going. The lone pair here on the base is forming a new bond to this proton. The electrons holding the H and A together are staying with the A, the conjugate base of that acid. So we're always thinking of these arrows in terms of electron movement, not atom movement. And there are 4 main ways that electrons move. Now, this isn't every type of step you'll ever see. There's a really interesting mechanism in chapter 9 that is different. But these 4 types are very common. Most reaction mechanisms that you are going to learn throughout this year will use some combination of nucleophilic attack, loss of a leaving group, proton transfer, or rearrangement. So here we're going to go through what those patterns look like. All right, so number 1, we have nucleophilic attack. Right? A nucleophile is attacking an electrophile. We're forming a new bond. So this can look a couple of different ways. As we talked about just moments ago, nucleophiles can be different, right? They can have full charges. They can just have lone pairs and be highly electron dense. They can be double bonds. They can be triple bonds. In this example, very simply have a negatively charged bromine and a positively charged carbon. Negative is attracted to positive. And if we look at the product, we see a new CBr bond has formed. If we want to be complete here, that bromine doesn't have a charge. So I know common bonding patterns, it has 1 bond and 3 lone pairs. So it went from having 4 lone pairs to sharing one of those pairs with the carbon. The carbon went from having 3 bonds and a positive charge to having 4 bonds and being neutral. So there's only 1 arrow needed, 1 bond formed, and that is it. It goes from the nucleophile to the electrophile. Notes here, the charge should wind up being the same on both sides of the arrow. On this side, you have a +1 and a -1, so it's neutral. On this side, it's neutral. The charge should always add up to the same overall from left to right. Okay. Everything about where your arrows start, stop, the direction, and the head is important. It's important in your homework. You've probably already gathered that if your arrow doesn't point to exactly where it should, the online homework isn't going to take it. When I give written tests, I'm just as picky because this is a sentence. This is a story. I can tell from that arrow that this lone pair on this bromine is forming a new bond to this carbon. It may also require more than 1 curved arrow. Okay, so it can be one or more arrows. Now, how do you know when you need more than one arrow? You will need more than one arrow to avoid breaking the octet rule. Usually on carbon, or any second row element. So for instance, when we're looking at this next example, there's an alcohol, and these specific reactions you don't need to worry about yet. We're going to look at each specific reaction in its own chapter. For instance, this reaction between an alcohol and an acid halide is actually from chapter 21, I believe. So we're just using it as an example here of this pattern. You have your nucleophile, your oxygen with a lot of electron density. You have your electrophile, which is this carbonyl carbon, right? That carbon is very electron poor. Electrophile, there we go. It's connected not only to oxygen, but to chlorine, right? So it's very partially positive. If we stopped at just drawing this first arrow, right, the negative oxygen with all of its electron density and its lone pair, forming a bond to that carbon, that would form 5 bonds on carbon, and that is too many electrons around carbon, right? That is breaking the octet rule for a second row element, which is not allowed. So one of the reasons we are allowed to do this reaction is this pi pair of electrons in the double bond. It can be moved out onto the oxygen, right? And that allows us to have this nucleophilic attack without putting 5 bonds on carbon, which is not allowed, right? And so you wind up at first getting this intermediate. All that we've shown is the new bond between the carbon and the oxygen. And we showed that this bond here, the pi bond, broke, and we wound up getting extra electrons on that oxygen up top. Now, that's not the end of that reaction. That reaction continues forward, but that's the first step. Remember, these are steps we are learning. Some reactions happen in one step. Some reactions happen in many steps. I think there is a reaction in organic too where there's like 9 steps. So it's important to learn these patterns because we're going to hook them together. This is like we're learning pieces of a bigger puzzle. Pi bonds can also behave as the nucleophile, as we mentioned. And so look at the similarity here. You have a lot of electron density on that double bond. That sulfur in the middle of sulfur trioxide is very electron poor. Sulfur is less electronegative than oxygen. And so it is being pulled in all 3 directions, and it winds up being a good electrophile. And so we form this new CS bond. You do see this going out. Now, sulfur can have more than 8 electrons around it. And so that second arrow maybe isn't as critical. But for each reaction mechanism we learn, we are going to discuss how many arrows go in each step. But that's the 3 different examples of nucleophilic attack. Sometimes the nucleophile has a full charge and it's very obvious. Sometimes it is just a lone pair on an electronegative element. And sometimes the nucleophile is a pi bond set of electrons. Now, the second pattern that we're going to see is loss of a leaving group. This will have a bigger discussion in chapter 7 on what constitutes a good leaving group, how do you know when they leave. But just for now, to recognize the pattern, loss of leaving group is kind of self-explanatory. You're losing something. A bond is breaking. In this case, this is a reaction right here that we'll learn towards the end of chapter 7. We are seeing an alkyl halide break apart. And this does happen spontaneously for certain alkyl halides. And so you're seeing that arrow go from the bond to the atom. What that is saying is the electrons holding that carbon and bromine together are leaving with the bromine, breaking that single bond. Now there's always some confusion after we learn resonance about arrows showing single bonds breaking. Now, you can't do that in a resonance structure because resonance is not a chemical reaction. Resonance is showing the electron kind of location on a molecule. This is communicating a reaction, and bonds do break in reactions. And so in this case, what I have drawn is just that bond breaking. So carbon went from 4 bonds to 3. Bromine went from 3 lone pairs and a bond to 4 lone pairs and a charge. Again, neutral, overall neutral. It is an equilibrium step because that bromine can very easily attack, right? You can have a nucleophilic attack and go in the other direction. But this is an important step for some reactions. And so we do recognize this as a loss of a leaving group. Sometimes this requires multiple arrows. You see that here. This is called, I think this is a Meisenheimer complex. This is from chapter 18. So this is another organic 2 intermediate. It's still loss of leaving group. It just requires some rearrangement in the electrons in the molecule. So you notice it's this cascade of electron density until ultimately you break that single bond. We will look at that in great detail when we actually get to that point. The third pattern is the proton transfer. So the proton transfer is your acid-base step, right? Is your Bronsted-Lowry acid-base step. And we see these all the time. We are going to be talking about acidic and basic steps throughout organic chemistry. It's why it gets its own review chapter in chapter 3. Here is an example of a proton transfer with a carbonyl, right? We are taking the lone pair of that oxygen, and this always requires 2 arrows unless you just have H plus written as shorthand, because the proton's always attached to whatever the acid is. And so you are going to show the new bond form between the oxygen and the proton, and then the OH bond break between the proton and the rest of the hydronium molecule. It can go in either direction, though. You could be transferring a proton to your organic molecule of interest, or you could be removing a proton. So you can see the carbonyl here is your base. It is accepting the proton, as opposed to, in this example, your protonated carbonyl is your acid, right? And it's donating a proton to the water. So anytime we are just moving a proton around, it fits into this category of proton transfer, typically 2 arrows. Always going towards the proton, at least in one of the arrows, right? You're never going to start an arrow at a hydrogen. Hydrogens don't have any lone pairs. And so if you start an arrow at an atom, it's got to be an atom with a lone pair, right? Or it's got to be at a bond. The arrow needs to start where there are electrons. And then your other arrow will come from breaking the bond that was holding the proton onto its acid. Occasionally, it can take a third step, plus if needed, right? And again, this often happens to avoid breaking the octet rule. So let's take a look here. Something we learn about in chapter, I think this is chapter 21 as well. Protons that are close to carbonyls are more acidic than you expect them to be. And so we have a proton transfer where a strong base comes in and picks up that proton. And you can draw this a couple different ways. You could draw it staying here on this carbon, and then you have a lone pair on your carbon, and there is resonance with that oxygen atom. Or you can show it all at once here. You can show the CC double bond being formed, but you cannot put 5 bonds on that carbon, so you have to kick the pi bonds up. Again, we will go through each of these steps individually when we get to these reactions, but it is good to recognize this is still just a proton transfer. We are taking a proton from our organic material and donating it to this base. And then the last group here is a rearrangement. We will see some rearrangements in Chapter 7. A rearrangement is typically going to happen to help stabilize a carbocation, so a carbon with a plus charge. It is not resonance. It is not delocalization of the charge. It is actually rearranging, so breaking a sigma bond, rearranging that ion to make a more stable ion. And so we need to discuss stability, right? To do that, we have a little bit of vocabulary we need to get into here. Carbon is not all created equal. What is attached to the carbon will affect its stability. If it is all hydrogens are not bringing any electron density to the party to help stabilize that plus charge. So this is the least stable. Every time that we replace one of those hydrogens with an R group, now remember, an R group represents carbon. It represents more organic compound. It is going to get more stable. If we put one R group, we call that a primary carbocation. 2 R groups and 1 hydrogen is a secondary carbocation. And 3 R groups with a plus charge is called a tertiary carbocation. The more R groups, the more stable. So 3 R groups is going to be the most stable out of these. When you have a carbocation, if it is one of the less stable carbocations, it may rearrange to make a more stable carbocation if it can. So let's look at when that is possible. Here we are going to talk about a 1,2 hydride shift or a 1,2 methide shift. It's important that you recognize the 1 and 2 are here to indicate you can only shift something from next door. You can't pull a hydride or a methide from across the molecule. It's got to be right next door. So when we look at this hydride shift, let me move this down. There we go. We're taking a carbocation that is secondary, and we are moving a hydride. Now notice, I'm not saying proton, and I'm not saying hydrogen. Because remember, a proton is H with no electrons. Hydrogen has 1 electron. Hydride is a hydrogen with 2 electrons. So both electrons are shifting. It's taking the hydrogen and both electrons in that bond and shifting over. And the reason it does that is because we go from a secondary to a tertiary carbocation, more stable. It won't go in the other direction. You will only rearrange to make something more stable. This can also happen with very small R groups. We're only going to worry about a methyl group. Again, we have a secondary carbocation. We don't worry about any of these hydrides shifting because it would make a primary carbocation. You will not rearrange to make something less stable. So here, we can't do a hydride shift. There's no hydride next door that would make it more stable, but there is a small methyl group. Same thing. The electrons holding those carbons together are going to shift. You are going to shift that entire methyl group over, and you are going to have a new tertiary carbocation. Right? So it can look like a hydrogen moving over or a methyl group moving over. And write this down, put it under your pillow, speak it to yourself at night. Shifts only occur to get a more stable carbocation. You do not just get rearrangements any old time. Now, when we look at reactions, now this is a reaction from the end of chapter 7. So we will talk about this in this unit, but it'll be in a couple weeks. We are taking an alcohol, right? If we just looked at the overview of this reaction, we are reacting it with hydrobromic acid. And we are getting an interesting product where there is no longer an alcohol, but there's a bromine, and it's in a different position. So instead of just thinking about this in terms of Gen Chem, okay, A and B make C, we are going to look at exactly how that happens. It starts with a proton transfer on the alcohol. Then you get a loss of leaving group when that breaks off as water, making a secondary carbocation, which then rearranges to make a more stable tertiary carbocation, and ends with a nucleophilic attack. These are the 4 patterns we just discussed all together. Now, this is not something I ever did. I always just memorized my mechanisms. But when I was teaching in summer school, so this is just a little tip from previous student. If you are having trouble memorizing mechanisms, having these steps numbered, so the way we did them, nucleophilic attack was number 1. Loss of leaving group was number 2, proton transfer was 3, and carbocation rearrangement was 4. And so when she had this list in her head, right, each step had a number. So when she came to this reaction of this alcohol making this bromide, she knew that her mechanism was a 3-2-4-1. So maybe she wasn't able to remember exactly what happened and memorize this picture, but she was able to memorize the pattern numbers. And I thought that was a really smart idea, because as we get to bigger mechanisms where we have repetitive steps, having any way to help you remember those mechanistic steps, I think is great. If you don't like that and you get confused about number patterns, then don't use that. But I like to share that with you because I thought that was such a smart idea. I had no idea what was happening until her first test came back, and she'd have these little codes written next to it, and I didn't think much about it. But on test 2, then I had 3 or 4 students that had these little codes, and I stopped them to ask, because it was pre-COVID. I watched them take the test. I knew they weren't talking, and they shared with me this strategy they were using, and I thought, man, that's so smart. They even broke it down farther. So I think Leroy's saying hi again. They broke it down into proton transfers into 2 different groups. Proton transferring like from the organic starting material or away. So I think she had a number system that was 1 through 5 away from the starting material. So was the organic acting as the acid or the base? Kind of, she broke those into 2 different ones. Again, if that doesn't make sense to you, you don't like it, don't use it. You don't have to. I'll teach you each mechanism individually. there is another situation that can happen here where two patterns occur at the same time. And that is really going to come down to you learning the reactions. In this case, the OH is replacing the Cl, and you are getting that nucleophilic attack at the same time that the leaving group is leaving. You can't have the nucleophilic attack happen first and by itself, because that would put 5 bonds on carbon. And you don't get the loss of the leaving group happening on its own here, because it would make a very unstable primary carbocation. So for some reactions, they will be a little bit more complex, where you will get two patterns happening at once. Again, that's why we go through each mechanism together. I do apologize for little Leroy. It looks like chapter 6 is just going to be a Leroy heavy moment. Yeah, go outside again. All right, so the slide that we're on here is just reiterating that you pay attention to where your arrows start, where they stop, the direction they're going in, and the head of the arrow. So the second arrow is drawn incorrectly here. Why is that? It's because it starts on this carbon. That carbon isn't going anywhere. That carbon doesn't have any lone pairs. So this arrow here doesn't make any sense. The arrow has to start where there are electrons. If you're trying to show this bond breaking, the arrow needs to start at the bond. This arrow is drawn correctly. It just doesn't have the explicit lone pairs. So if you see an arrow drawn from an atom, it doesn't mean it's wrong. It just means that there has to be lone pairs on that atom. If there are not lone pairs on that atom, the arrow should not start there. Where it is going, right? We see this a lot. Putting in your explicit hydrogens can be helpful, because you can draw an arrow to an atom, but you don't want to violate the octet rule on a row 2 element. And so that's why in this particular reaction, we have to have the nucleophilic attack happen with the loss of the leaving group. Because if we leave this as is, that is indicating that for some moment in time, that carbon has 5 bonds, and that is not going to happen. Okay, so just summary here. I will tell you, if you're new to using Klein provides excellent summaries at the end of his chapters. And so if you are not somebody who finds reading the entire chapter useful, might I suggest going in and reading those overviews and summaries at the end of the chapter. Oftentimes there's a lot of great graphics and tables, and you have access to it in Wiley Plus, so I really recommend doing that. There's practice on rearrangements. There are things to consider about if you're going to rearrange something, you want to make sure it's going to make it more stable. You will see resonance coming into play there. We'll talk more about that when we actually do some reactions that have rearrangements. We talked a little bit about this in, I think, part 1. Reaction steps sometimes get an equilibrium arrow and sometimes get a forward arrow. This is determined by kinetics and thermodynamics. And I'm not a stickler for those when you're doing a mechanism, as long as you're moving it forward. So sometimes you'll see me use irreversible arrows where maybe Klein used reversible. As long as you're not throwing a resonance arrow in when it's supposed to be a mechanistic arrow, I'm fine with that. There are tips and tricks on when to think, when you have an irreversible step versus reversible. I don't want you to focus on that. So that's why I'm just skipping through that rather quickly. And we're going to keep skipping through that. Also, if it is a proton transfer, whether or not you get a reversible or irreversible arrow very much has to do with how different the pKa's are. So we know that equilibrium will favor the weak side. Well, how weak is it in comparison? 15.7 versus 50 is a huge difference. You tend to get an irreversible arrow. 15.7 versus 18, much closer together. Much more likely you're going to have a significant amount of both sides present. You don't have to know the pKa's. Unless I give you the pKa's, you don't have to worry about calculating them. Rearrangements are irreversible because you're only going to rearrange to make something more stable. So if it rearranged, it's now more stable. It's not going to go back. We will occasionally talk about Le Chatelier's principle, something you learned when you talked about kinetics in Gen Chem. When it comes up, I'll certainly review it with you. There are ways to manipulate reactions to get more product, and that may be adding more starting material, removing product as it's made, adding heat, removing heat, changing pressures. There are things we will refer to. If Le Chatelier is not a word you've ever heard before, that might be something you want to review from chapter 1. I will review it as we go forward. And sorry for 2 longer videos, but really chapter 6 is just a primer for chapter 7. And so I wanted to make sure I got it all done here in this part 2. I will see you in not part